Chapter 6, Osseo, Tissue, and Skeletal Structure. Primary functions of the skeletal system, there are 5. The first one is support, which provides structural support for the body. Storage of minerals such as calcium and lipids in the yellow bone marrow cavity. Blood cell production, all types, red, white, and platelets. Protection of surrounding organs and soft tissues, and leverage so they can change the direction and magnitude of the forces generated by the skeletal muscles to do work. Bones are classified according to shape. We have 6 different shapes: sutural bones, irregular bones, short bones, flat bones, and long bones. The last is the sesamoid bones. Sutural bones, the first type of bones that we're going to talk about, are also referred to as wormian bones, and these are formed between the sutures of the skull. When you are first born, the bones of the skull are not completely fused, and once they do fuse with sutures, sometimes they form like a little island of bone that's isolated by the suture itself, and that becomes a separate bone. Irregular bones are bones that have a wide variety of extensions or shapes coming off the bone. They are found in your vertebrae and your pelvis area. Some of our facial bones will also be irregular in shape. Short bones, the next classification, are small, boxy, kind of square-like bones. They make up the carpal bones in your wrist. Also, some of the tarsal bones of the ankle are short bones. Flat bones are thin bones. They have parallel surfaces. They are made with a lot of spongy bone in between the two surfaces, and you find these in the skull bones as well as other places. Long bones are relatively long. They're slender. They're going to make up the long bones in the arm and the legs, the palms of your hands, the forearms. The last bone classification is the sesamoid bone. These are small, round bones that are usually found in your joints of your hands and your knees. They develop inside the tendon, and the most common one that everyone has is the kneecap or the patella. 2 types of bone tissue are the compact bone and the spongy bone. The compact bone is dense. It's located on the surface of the bone, making up the shaft of the long bones. The spongy bone, also called cancellous bone, is at the ends of the long bones or between the thin flat bones, and it is made up of a network of struts, bony struts, and plates, and in the interior of the spongy bone is where you will find the red bone marrow. Okay. The anatomy of a long bone. We'll discuss the different parts of the long bone. The epiphysis is what the ends of the bone are called. There are 2 epiphyses, and in this area you will find spongy bone located in those epiphyses, and this will house the red bone marrow between the bony struts of the spongy bone. The diaphysis is the shaft of the bone. It has the medullary cavity in the middle, and in the medullary cavity you will find the yellow bone marrow, which is lipid. In between the epiphysis and diaphysis you have a metaphysis. In this area will be the growth plate, the epiphyseal plate, and which is cartilage, and once it has completely ossified, it will be called the epiphyseal line when you're mature and have reached maximum height. Okay. Other parts of the bone surrounding the ends of the spongy bone, where at the epiphysis is a thin layer of compact bone, which is called the cortex. And then we have outside the bone a membrane called the periosteum, which is a double layer membrane that will provide protection and bone growth. New cells will be produced in the periosteum. And lining the medullary cavity we have the endosteum, the inner membrane, that will have cells for bone growth as well as breaking down bones when necessary. Okay. We also have in this figure the flat bone, and you can see that the flat bone is got a very thin layer of compact bone called the cortex, just like around the ends of the epiphysis. and the spongy bone with its bony trabecula, where the red bone marrow will be located. Also on the bone is the articular cartilage at the ends of the bone, where one bone will touch another. Where they touch, it's called an articulation, and there will be cartilage on each end that will protect the bone. Okay, under bone histology, the osseous tissue is a type of connective tissue. This is your bone tissue. The matrix is very solid and sturdy, and it is that way because it has calcium salts that are located around protein fibers. The calcium salts are called hydroxide, calcium hydroxide and calcium phosphate. Both have the salts in there. Those salts form crystals, and the crystals are called hydroxyapatite. These are going to then adhere to the collagen fibers, and they will then stick to it and form a nice crystallized mass on the collagen fibers. This is going to make bone both very sturdy and strong, but yet it's slightly flexible, so that if you bang your arm against a hard thing, it doesn't shatter. It might get hurt, but it doesn't shatter. Okay. When we are talking about the bony structure, initially when a bone is first made, it is, instead of having a nice calcified material, it has a gel-like matrix made of collagen fibers and glue, and this gel-like matrix is called osteoid. This will provide the framework where those hydroxyapatite crystals form, and this will allow the fibers to become very strong and sturdy, and the bone is resistant to shattering. Bone cells. There are 4 types of bone cells. We have talked about osteocytes so far in class. The osteocytes are the mature bone cells that live in the lacunas, which are the little housing units that are in the structure is embedded in the lamella, the concentric layers that go around the central canal. The osteocyte lives alone. Once it is completely calcified into his little housing unit, the lacuna, that lacuna is completely built. The osteocyte cannot divide, and it communicates with other osteocytes in their lacunas through small canals called canaliculi. These are little passageways that penetrate through the lamella, and then there's a cytoplasmic extension from one cell to the next, and they communicate through gap junctions at the end of the cytoplasmic extensions. So they can talk back and forth using nutrients and dissolved substances, electrical impulse, okay. And they can also be connected to some extent with the central canal. Okay. The main functions of the osteocytes is to maintain and monitor the protein and mineral content of the matrix, and they can participate in repair if there is damage to the bone. The second type of bone cell are the osteoblasts. Blasts are builders. These are immature bone cells that are building the lacunas, and once they make the lacuna and calcify themselves completely within the lacuna, they become the osteocytes. They're grown-up immature bone cells. But if the matrix is broken, if you break your bone, then the osteocyte can convert back to an osteoblast to help with repair of the bone. The process of making new bone is called osteogenesis, and that is the function of the osteoblasts. They do this by increasing the concentrations of calcium and phosphate and the calcium salts, and converting the osteoid, which is a gel-like matrix, into a calcified bone-like matrix. The third type of bone is the osteogenitor. The osteogenitor is the stem cell that divides to produce daughter cells that differentiate into the osteoblasts, which grow up to be the osteocytes. So those 3 cells, the osteogenitor, the osteoblast, and the osteocyte, are all from the same cell, so they're all closely related. Okay. Your osteogenitor is going to be very important when you have bone fracture, because they will help with assisting in developing new cells to fill in the area where it's been broken. You're also going to find them located in the intercellular layer of the periosteum, that outer membrane, the inner layer in the endosteum, that lines the marrow cavities, and these areas is where they will be involved with cell division and producing new bones. The fourth and final type of bone cell is called the osteoclast. He is not related to anyone else. He is a giant cell that has 50 or more nuclei, closely related to macrophages and their stem cells, and the osteoclast's job is to break the bone back down. So you have the blasts that are building and the clasts that are breaking it back down. This is going to be involved in osteolysis, when they do resorption of the bone and they put that back into the blood. So this is, along with the blasts, are going to constantly be in a tug of war if you're maintaining your blood calcium level. If the calcium level gets too low, the osteoclast will take it from the bone. If the calcium level gets too high, the osteoblast will store it in the bone. So they're going to constantly be moving the calcium in and out of the cell. This is a picture of the osteons showing a number of osteons. These are the major functional unit of the compact bone, and we will discuss their structure next. So the osteons, the functional unit of the compact bone, are made up of a circular structure, sort of like a little apartment complex. It will have concentric layers of calcified material called concentric lamella, which will all go around the central canal. The central canal will provide the blood vessels and nerves and lymphatic vessels that will maintain the different osteocytes. The osteocytes live in little holes called lacunas, which are located within the concentric lamellae. And also, besides the central canal, we have perforating canals, which are going at a perpendicular angle so they can go deeper into the osteon and feed the osteocytes that are farther away from the central canal. Now the layers are called lamellae of calcified material. So we have the concentric lamellae that make up the circular layers in the actual osteon. In between two osteons, we will have interstitial lamellae, which will fill the space between the two so there's no holes within the bone. And then surrounding the whole bone, we will have circumferential lamellae. This will then be covered with the periosteum. The function of the compact bone is to be thick, and very thick, where stresses arrive from a limited range of directions. So it can take a good hit if it's going straight down the compact bone, whatever the stress is, but if the stress comes at an angle to the compact bone, then it can break much more easily. This figure is just a figure of a single osteon, so you can see it a little more clearly with the central canal and the blood vessels. The central canals are lined by endosteum so that it can produce new cells when needed. And you have the concentric lamellae with the osteocytes living in the lacunas, and you can see the canal iculi where they can communicate. Spongy bone is found in the epiphysis of the long bone or in the skull bone, the flat bones. Your spongy bone is made up of bony struts that are called trabeculae. These give it a lot of holes in the spongy bone. They are covered with endosteum. There are no capillaries in this matrix, so that the nutrients have to diffuse through the endosteum to the osteocytes located there. And in between the trabeculae is where you will find your red bone marrow stored. Your red bone marrow produces red blood cells, white blood cells, and platelets. Your compact bone will manage stresses that are applied in one direction only along the compact bone, such as in the long bone, running the long distance down it. So if you get damage there, it's hard to break your femur. But if somebody hits you from the side and hits it in a perpendicular manner, it is not as hard to break the femur because the long bone is not constructed to take stresses at that angle. Your spongy bone is better at taking stresses from a variety of angles. It's not as strong as your compact bone, but it gives a little bit more of support in areas where there's a lot of twisting or torquing, such as the ends of the bones, where they might form the joints. The spongy bone also is going to help with decreasing the weight of the body. There are two membranes on the bone or in the bone that we're going to talk about. The periosteum is the external membrane. Peri means peripheral, to the outskirt. It surrounds the outside of the bone. It is made up of 2 layers. The outer layer is dense, fibrous connective tissue for protection. The inner layer is cellular layer for division of new cells to produce new bone matter and laying it down on the outside of the bone. Its function not only is bone growth, but it isolates the bone from other organs, and it will also attach the blood vessels to it, so it provides a route for blood vessels and nerves so they stay close to the bone itself. The second membrane is the endosteum. Endo means inside. This is going to be found inside the medullary cavity, and it will be found on the trabecula. And this is going to be very actively involved in bone growth and repair the bone and remodeling. It will house on this single layer of membrane. It will have mostly osteogenic cells, but there will be some osteoblasts and osteoclasts. So we're going to be busy building up bone or possibly breaking the bone down with the cells of the endosteum. Bones and the skeleton begin to form about 6 weeks after fertilization, and growth continues until 25 years of age for some of your bones. The last bones to fuse together and finally stop growing are in the hip area. The coxal bones, or os coxa, are the last to fuse. Now, with bone formation, it is called osteogenesis. Osteogenesis requires us to do ossification, which is the process of replacing other tissues with bone. We start out with an osteoid, gluey-like material, gluey gel material, and then that undergoes calcification, which is when you deposit the calcium salts, and that is the process of ossification, changing another type of tissue into a calcified bone tissue. There are 2 types of ways that the bones will be produced. These are different types of ossification processes, and they occur in different types of bones. The first is the intramembranous ossification, and this will occur within the flat bones of the skull. You'll have numerous ossification centers where it starts with ossification and then eventually it will all fuse to form the bone. And in the ossification centers you have mesenchymal cells. Those are the stem cells of all connective tissues. These stem cells in intramembranous ossification directly develop into osteogenic cells. Then those osteogenic cells will develop into osteoblasts and then mature into osteocytes. The bony matrix forms the trabecular spongy bone, and the outer layer will be compact bone, and it will eventually develop a periosteum on the outside of the bone. So the most important thing about this type for you guys to remember is that it's directly from stem cells to some type of bone cell itself. The second type of ossification processes is endochondral ossification. And this is when the bone develops from a cartilage model. The endo means inside, chondro means cartilage, so we have a nice bone made just of cartilage, and then it will slowly undergo a change to change the cartilage into bone. Okay? You're going to start with mesenchymal cells. They're going to develop into chondrocytes to make the model, and then in the middle of that bone you will have the die-off of the chondrocytes, and they will be replaced with osteocytes. First the stem cells, the mesenchymal cells will give rise to osteocytes as a blood vessel and vascular tissue becomes available, because remember, your cartilage is avascular. It will form initially, the middle area will be filled with spongy bone in the in the diaphysis, and then that spongy bone will be broken down, leaving behind the medullary cavity and a layer of compact bone in the diaphysis region. The ossification in the diaphysis is called the primary ossification center, and then we will have a secondary ossification centers, and there will be 2 of those located in each of the epiphysis. They will do the same process of the cartilage will die, and then it will be replaced by bone cells, which will give rise to spongy bone. But here the spongy bone will stay. It will not be broken down, making the 2 epiphyses consist of spongy bone. Also, we do not get rid of all of the cartilage. We leave a layer of cartilage on the end of the bones that form the articular cartilage, and we leave a layer of cartilage between the epiphysis and the diaphysis, in the metaphysis area, that will be the growth plate and will allow for further growth until you hit maturity at puberty, and then that growth plate will completely solidify, and the epiphyseal plate is now called the epiphyseal line. Bones are highly vascular, so we have a number of blood vessels, arteries, and veins that will provide nutrients and oxygen to the bone. They are all involved with regulating the oxygen nutrient content to different parts of the bone. Looking at the long bone, we have 4 different major artery-vein combinations. The nutrient artery and vein will extend the length of the shaft and will feed all of the cells in the osteons of the compact bone. The metaphysis area will be taken care of by the metaphyseal artery and vein, where it will provide nourishment to the epiphyseal plate. The epiphyseal artery will provide nourishment to the epiphysis itself and the articular cartilage. And the periosteal artery and vein will supply the blood to the periosteum and any superficial osteons. Bone structure is going to be affected both by nutrition and by hormones that both will control and have effects on the bone growth and how strong the bone is. Calcium, under nutrition, calcium and phosphate salts, we need those in the diet for the bony matrix. Vitamin C is necessary for collagen synthesis, as well as to cause the osteoblast to differentiate to become osteocytes. Vitamin A will stimulate those osteoblasts to get to work and produce bone. Vitamins K and B12 are needed for protein synthesis within the bone. And vitamin D3 you need so you can absorb calcium and phosphate in the small intestines. Hormones have a large effect on your bone growth and maintenance. The first hormone is calcitrol. This is the hormone that's produced when vitamin D3 is converted to it in the kidneys. And calcitrol works to promote the calcium and phosphate absorption in the small intestines. The next 2 are growth hormone and thyroxine. These both work in similar ways. They both stimulate the osteoblast activity, which is going to synthesize more bone. Your sex hormones, testosterone and estrogen, are also going to affect the bone growth. They are produced at puberty, and then they stimulate the osteoblast activity in the epiphyseal plate. They're going to start increasing calcification in the epiphyseal plate, and the calcification will occur quicker than putting down new cartilage, so eventually it will completely pave over the epiphyseal plate, and once that is completely ossified, you have reached your maximum height, and the epiphyseal plate leaves behind just a little scar called the epiphyseal line. The next 2 hormones are going to work against each other. Many hormones do this, and they work against each other to maintain homeostasis of the blood calcium level. Your parathyroid hormone is going to react when the blood calcium level drops, and it's going to work to increase the blood calcium level. And the calcitonin hormone is involved with decreasing the blood calcium level when it is too high. Your blood calcium has to be maintained by homeostasis. We really cannot have too much of a fluctuation, otherwise it can lead to lethal conditions. So the 2 hormones that do this are going to work against each other, and this is parathyroid hormone and calcitonin. The parathyroid hormone is going to increase the blood calcium level when it gets too low, and it does this by having the osteoclast start working hard to remove calcium from the bone, by increasing the rate of calcium absorption in the small intestine, and by decreasing the rate of excretion in the kidneys of the calcium. So this way we're taking the calcium out of storage, we're absorbing as much as we can, and we're not throwing anything away, so the actual calcium level in the blood will increase. The second hormone, calcitonin, will decrease the blood calcium level if it gets too high. You can think of it, tones it down. Calcitonin tones it down. It's going to do this by decreasing osteoclast activity, so it's not releasing calcium from the bone, by decreasing absorption in the intestine, so some of it will be getting thrown out, and increasing excretion by the kidneys, so even more of it. If we don't absorb it, we're going to throw it out. Will be lost. Those three things will decrease the calcium level in the blood. Calcium is the most abundant mineral in the human body. It's 2 to 4 pounds. It's important for your nervous system, for your muscular system, and if we have any major decreases or increases, we will have problems. If it decreases by 35%, the neurons become excitable, they go into convulsions. If it decreases, if there is a calcium concentration of an increase of 30%, the neurons start to become unresponsive. You get a 50% decrease and you will have death. Because it is so critical, we rarely have more than a 10% fluctuation on a daily basis. When you break a bone, the first thing that happens is, due to all of the broken blood vessels, you have a lot of blood loss and you form a fracture hematoma, which is a blood clot. Bone ends where it's been broken the cells will die, and you'll now have dead bony fragments within the area. The beginning of repair starts with the endosteum, the membrane that lines the medullary cavity, and the periosteum, the membrane that lines the outside of the bone, starting to undergo rapid mitosis to connect the two damaged ends, try to stabilize it. Also, the cartilage will start to fill in between the two ends of the bone that are where it's broken. It's again to stabilize it. It will form a large lump internally and externally. Internally it's called the internal callus. The bump that you can see externally is the external callus. Okay. The bone that will then start to form from the cartilage. The cartilage will be remodeled into bone, and you will form bony struts such as spongy bone holding the bone together. Now this will be both external and in the middle of the bone, and now you're going to have to spend time doing remodeling. You're going to have to take those bony struts and convert them to compact bone externally. They're going to be broken down for the medullary cavity to be able to be a solid cavity, continuous, that will then be filled with yellow bone marrow. Okay, last area of this chapter is, what if you get an injury and you fracture your bone? There's a number of steps that are going to occur that will slowly cause the bone to heal and return it back to normal. Very first step, you're going to form a blood clot called a fracture hematoma, because you don't want to have a large amount of blood loss, as well as you will have inflammation occurring. The second step, we want to do a quick fill. So the cells of the periosteum and the endosteum are going to start undergoing rapid mitosis to try to connect the two ends with those membranes. And the cartilage model is now going to be put back in place. We're going to form cartilage really quickly from the mesenchymal cells. Later we will convert that cartilage to bone, but right now we just want to put a plug in there. After we've got it somewhat stabilized, we will now start to convert the cartilage to bone through osteogenesis. And from the cartilage we develop the osteogenic cells that develop into osteoblasts. They start to produce some bone matter, mostly the matrix. At this point, the wound is now filled with solid bone. We have not recreated the medullary cavity. It is still just filled with bone. It's just to stabilize it. At this point you can take the cast off, but you still have months ahead of you of remodeling. Also at this point you will see that there's a large collar around the bone, an excess area called the external callus, that will remain there. It may remodel, it may get a little smaller, but usually you can see where the bone has broke, and if you look at an x-ray, and it is much stronger than it was before it was broke. So you might re-break it, but you'll re-break it in a different area. Aging of your skeletal system. Osteopenia is a natural process of bone loss that's just due to aging. Your bones slowly get thinner and weaker because you're not doing ossification as well. Your osteoclasts are working faster than your osteoblasts are. And this will start 30 to 40 years of age. And it was a natural loss. Women will lose about 8% per decade. Men will lose only about 3% per decade. This is happening to everyone. Osteoporosis is an actual medical condition that will cause excessive reduction of bone loss, and this will compromise normal function of your organ systems. This is a genetic condition, so if your parents have it, or grandparents, there's a better chance that you may be at risk for osteoporosis.